What if a computer could solve problems that are currently unsolvable? Quantum computing is becoming a reality, with breakthroughs that elevate it beyond mere science fiction. Classical computers struggle with immense datasets and complex calculations, while quantum computers can perform calculations at astonishing speeds. Tasks that would take traditional computers years are becoming feasible. At its core, quantum computing leverages principles of quantum mechanics. Unlike classical bits that are either 0 or 1, quantum bits or qubits exist in superposition, allowing them to represent multiple states simultaneously. Coupled with entanglement, where qubits can influence each other instantaneously, the possibilities expand dramatically. The implications are both vast and profound, beginning to address problems we are just starting to comprehend. The current landscape features innovation from major players like IBM and Google, who are racing to develop powerful quantum processors. IBM's Quantum Hummingbird, introduced in 2021 with 127 qubits, positions the company as a leader. Startups worldwide are also contributing, driving the rapid evolution of the field. Quantum computing will enhance computational power and redefine our approach to numerous challenges. As quantum technology progresses, its implications ripple across various sectors. In pharmaceuticals, traditional drug discovery methods require extensive time frames and resources. Quantum computing can process vast datasets simultaneously, promising to accelerate this process significantly. D-Wave Systems is pioneering quantum annealing techniques that could redefine optimization problems in drug development, reducing the time and cost of bringing new medications to market. However, the transition to quantum computing presents challenges. Current quantum processors are still developing, and maintaining qubit coherence presents technical hurdles. IBM plans to build a 1,121-qubit processor named Condor by 2023, aiming for quantum advantage where quantum systems outperform classical computers. Google's Sycamore processor achieved quantum supremacy in 2019, solving a problem in 200 seconds that would take the world's most powerful supercomputer over 10,000 years. Yet, this highlights the narrow scope of current capabilities. Researchers are racing to refine quantum algorithms that can leverage qubits' unique properties. Startups like Rigetti Computing and IonQ are developing quantum hardware and cloud-based platforms, democratizing access to quantum resources. Rigetti's quantum cloud services allow businesses to experiment with quantum computing applications across various fields. Each quantum architecture, from superconducting qubits to trapped ion qubits, presents its own advantages and trade-offs in performance and reliability. The timeline for scalable quantum computing remains uncertain. Predictions differ, with some experts expecting breakthroughs in a decade, while others foresee a longer path. Optimism surrounds advancements in quantum error correction, which could facilitate practical applications. As organizations explore quantum solutions, they must navigate ethical considerations, especially regarding encryption, which will require new quantum-resistant algorithms to safeguard sensitive data. Environmental impacts must also be considered. The energy requirements for quantum operations, particularly for maintaining qubit coherence, pose sustainability concerns. Research into energy-efficient designs is essential as the industry scales. Quantum computing stands on the brink of revolutionizing multiple fields, promising unprecedented problem-solving capabilities. With continuous innovation from key players, the question shifts from if quantum computing will impact our lives to when it will. As this uncharted territory unfolds, the convergence of innovation, ethics, and societal impacts will shape the trajectory of quantum technology. The next few years will be critical as the race to realize quantum computing's full potential unfolds, reshaping our understanding of computation and its role in human progress. In 1981, physicist Richard Feynman first proposed the concept of a quantum computer, arguing that classical computers could not efficiently simulate quantum systems. This revolutionary idea marked the inception of a field that would take decades to materialize. Fast forward to 1994, when Peter Shor developed a groundbreaking algorithm capable of factoring large integers exponentially faster than the best-known classical algorithms. This insight laid the groundwork for the application of quantum computing to encryption and security, raising questions that are still being addressed today. The journey from theory to practice gained momentum in the early 2000s. In 2001, IBM, and Stanford University successfully demonstrated that a quantum computer could execute a simple algorithm on 3 qubits, a pivotal moment that highlighted the potential of quantum technology. Imagine a lab filled with the hum of machinery, the glow of screens displaying quantum states, as eager researchers look on, with expressions of cautious optimism, as they run their first algorithm. Yet, the practical challenges loomed large. Building a functioning quantum computer is akin to constructing a delicate ecosystem. Every qubit must be isolated from noise, a feat that becomes increasingly complex as more qubits are added. Fast forward to 2019, the year Google announced it had achieved quantum supremacy with its Sycamore processor. But what does this mean? Imagine a state-of-the-art facility, bustling with scientists and engineers, meticulously calibrating their quantum processor, a sleek array of superconducting qubits. Each qubit is housed in a frigid chamber, cooled to near absolute zero, a space where quantum mechanics can truly shine. The moment they announced the 200-second solution to a specific problem, a task that would take the most powerful classical supercomputer over 10,000 years, it was a historic milestone, reverberating throughout the global scientific community. Yet, the excitement was tempered by the realization that this was only the beginning. The problem solved was narrow, designed specifically to showcase the power of quantum computing rather than reflect its versatility. Researchers, motivated by that milestone, started envisioning broader applications, from simulating complex molecules to optimizing supply chains. Imagine pharmaceutical companies, once constrained by classical computational limits, finally having the ability to model protein folding or drug interactions in real time. The implications for healthcare are staggering, with the potential to significantly shorten drug discovery cycles and improve treatment efficacy. As these advancements unfold, startups are emerging as key players in this evolving landscape. Rigetti Computing, founded in 2013, is one such company, focusing on building practical quantum processors. Picture a startup environment buzzing with energy, engineers huddled around quantum chips, iterating on designs, and developing cloud-based quantum computing platforms. Their quantum cloud services open doors for businesses eager to experiment with quantum applications, democratizing access to technology that was previously confined to elite labs. Meanwhile, IonQ, a pioneer in trapped ion quantum computing, has made strides by emphasizing user-friendly interfaces for quantum programming. Their systems allow users to leverage quantum computing power without needing deep expertise in quantum mechanics. Imagine a small business owner sitting at a computer, utilizing IonQ's interface to optimize logistics through quantum algorithms. Such accessibility paves the way for innovation across industries previously thought unreachable. But with these advancements comes significant ethical and societal implications. Quantum computing's potential to break current encryption standards raises concerns in cybersecurity. With traditional encryption relying on the difficulty of factoring large numbers, the arrival of powerful quantum algorithms poses a direct threat to data security. Governments and corporations must now grapple with the need for quantum-resistant algorithms, a race against time to protect sensitive data in an increasingly digital world. On the sustainability front, the energy demands of quantum computing are not trivial. Maintaining qubit coherence requires extreme cooling and precision, often leading to significant energy consumption. The industry must pivot towards energy-efficient designs, exploring alternative methods that could minimize the carbon footprint of quantum operations. Research is underway to develop systems that can operate at higher temperatures and utilize less energy, ensuring that the advancements in quantum computing do not come at the expense of our planet's health. Looking ahead, the timeline for practical, scalable quantum computing remains a topic of debate among experts. Some foresee a decade of breakthroughs that will revolutionize industries, while others caution that the path could be longer and fraught with challenges. Optimism surrounds quantum error correction, a crucial aspect that scientists are racing to refine. Error rates currently hamper the reliability of quantum computations, but advancements in error-correcting codes could enable practical applications sooner than anticipated. As organizations explore quantum solutions, they face a myriad of questions that intertwine with technological advancement. How will society adapt to the changes brought by quantum computing? What measures must be taken to ensure equitable access to this transformative technology? As we navigate this uncharted territory, collaboration between technologists, policy